let's talk about how we measure angles. Many of us are familiar with the degree measure of an angle, which says that a full revolution of an angle is 360 degrees. And you might ask where that number comes from. If you haven't asked that before, I think it's an important question to ask. Why 360 degrees? And it is important to note that all units that we have are chosen. They are chosen by humans. And so, people think of the foot and the cubit as being these very arbitrary chosen measurements. But really, all of our measurements are arbitrary chosen measurements. Okay. So nobody really knows definitively why we chose 360 to be the number of divisions of a circle for an angle measure. But some likely choices, or some likely explanations, are possibly that, well, it is pretty easy to divide a circle up into 6 equal pieces. Using a compass and straight edge, I think I should have had another. Let me see if I can grab. Okay, I'm gonna do this. So you can easily divide with a compass. So I'm simulating a compass here. You can imagine a compass where you stick a needle in the page here, and then you have a pencil that traces around, and you can draw a circle. And so I can then put a center at this point and use the same radius. And then I can put a center at this intersection and use the same radius. And I can keep doing this. And that will get me 6 even divisions around the circle. Okay. And so it is easy to see that you can actually easily you can tile the plane with equilateral triangles. Okay, so if I was to let's see, is there a way to hide those circles? Select. Okay, so I'm gonna hide these circles, and then but those were what actually gave us our construction. And so it is easy to see that you can, with a very basic tool, the compass, you can easily divide a full revolution into 6 equal parts. So there's that. And then, in the degree measurements, we would actually have 60 degrees in each one of these angles of a triangle. And the reason potentially for wanting 60 degrees there is, 60 is a really nice number that is divisible by a lot of numbers. And so it is divisible by 2 and 3 and 4 and 5 and 6. It's not divisible by 7. It's not divisible by 8. It's not divisible by 9. It's divisible by 10. 360, though, is divisible by all the numbers from 2 to 10 except for 7. Okay, so it's divisible by 2, 3, 4, 5, 6, 8, and 9, and 10. So it's very highly divisible. So there is a convenience to the 360. Okay. And it's pretty finely granular. Another suggestion for maybe why we do 360 for a revolution is because on Earth, our yearly cycle is close to 360 days. Okay. So nobody knows for sure, but those are the basic guesses. The one being that we want to divide into 6 triangles, and then each triangle is just convenient to have them have 60 parts in them. Another one being this sort of Earth-centric view. Okay, but the degree measurements are, in fact, an arbitrary decision. So another way of defining an angle measure is to look at the parts of the circle. So in a circle, we define a circle by basically 2 parameters. Usually we have the center of the circle and the radius, which is the distance from the center to any point on the circle. Okay? And so one very convenient way of defining an angle measure is to look at the arc that is subtended by that angle and ask yourself how many radius lengths there are in this arc. So it would be a curved length. And so I'm going to drag this out. So this right here would be approximately 1 radius length here. And I'm going to drag this out here. And oops, right about there looks like 2 radius lengths. I have them highlighted in colors. And so there's 3 radius lengths. So this angle would be 3 radius lengths. And so we would give this angle an angle measure of 3 under this measurement system. Okay. And notice that angle measure, the angle measure really just tells you how wide open these legs are from each other. And it doesn't say anything about the lengths of the legs or the size of this circle. So, I mean, I can make this circle smaller, but the angle is the same angle. Okay, it still has 3 radius lengths there. Okay, so then this angle, let's see if I got actually 3. It's almost 3. So this angle would be approximately 3 radians. Okay, because in this arc length is approximately 3 times whatever the length is of the radius. All right, so that is the idea of radian measure of an angle, is it's just counting how many radius lengths does it take to go around the arc of the circle to cover that angle. Okay, so now you might know that so you might want to stop and think about this if you don't know right off the top of your head. How many radius lengths does it take to go all the way around the circle? I'm going to close this up and let you think about this. How many radius lengths does it take to go all the way around a circle? So, you might know that there are 2 pi radius lengths to go all the way around the circle. In fact, the definition of pi is basically how many diameter lengths it takes to go all the way around a circle. That's what the definition of pi is. It's how many diameter lengths go around the circle. So a diameter is 2 radiuses. So the diameter would be 2 pi radius lengths, or sorry, the full circumference of the circle would be 2 pi radius lengths, which is approximately 6.28. Okay. So that tells you that the angle measure of one full revolution is 2 pi, and the angle measure of a half a revolution is 1 pi. All right. Now, this is a good way to remember your different points of angles. So pi is basically a straight angle. Okay, the straight angle is where you have, I want to not reference degrees. A lot of people will say, oh, that's 180 degrees. I would like for you to start really thinking in radians and not revert to degrees. So pi is a half turn. Pi is a straight angle. Okay. Then a right angle is half of a straight angle. So that would be what? That would be half pi. Okay. And so you can take all of your other measurements of radian measure, basically starting from this is pi. Okay, knowing this is pi, this is 2 pi, and everything else is a fraction thereof. I'll try to make another video to cover that, to clarify what all of the different fractions of pi would look like on the unit circle.